please. Yay. Okay. So we took data for books. The little column of gas kept shrinking as we applied pressure, which is no surprise because according to Boyle's law, we know that as pressure increases, volume will decrease. So the volume of our gas decreased as pressure increased. So I'll pull the books off. And so we collected our data, and then we found the inverse. So basically, the gas column started out at 72 millimeters. 1 over 72 is this little fraction here, this decimal. And so we found the inverse for all those and filled our chart in. And here's the chart you'll need for the worksheet. Okay, so then what we need to do is draw a graph and see what we can learn. So we've got an x-axis filled out, and the label on the x-axis needs to be pressure in books. Always label your axes. Pressure in books. So we collected data from 0 to 6 books. And then we're also going to include a negative axis. But graphing the y-axis, this 1 over v column is the y-axis, is more challenging. So we need to find the range of, yeah, no, not that. Oh, goodness. Here, Bun, help point. So the range of this. So what you do to find the range of your y-axis is you just subtract the one end from the other end. So 0.0270 minus 0.0139, right? Is going to be this. This is the range of my axis. So then I look at my graph paper and I think, well, actually, no, that's not what I want to do. I actually want to start at 0. I want to start at 0. So my range is just going to be 0 to 0.0270, right? So 0 on the y-axis will be here, and 0.0270 will be here. All right, so here's how I deal with hideous decimals on a graph. 270, hooray!
Oh, that's nice.
Yeah. So now my range is 0 to 270, right? Which makes a lot of sense. So now what you need to do is look at where your y-axis is and decide what you can count by to fit on the page. Like I counted by tens because I put my x-axis at the exact bottom of the graphs. If you didn't put your x-axis at the bottom of the graph, you can flip the paper over and start over. Or you can count by 20s. But you know, when you graph, here's what you can't do. You can't say 270, 241, 213, right? You can't evenly space numbers that aren't evenly spaced. This is not how you graph stuff. You don't just plot your data up and down the y-axis. You make the y-axis evenly spaced. So 10, 20, 40, 50, 60, 70, 80, 90, 100, 30, 40, 50, 60, 70, 80, 90, 200, 10, 20, 30, 40, 50, 60, 70. So 270 will have it right there. There's no good way to label your axes on this graph because they're always going to be in the way. So. And of course the graph paper keeps you guys honest. Mine are kind of crammed in there. Okay, so once you have it labeled, then you could actually go back in and put the 0.0 and make these back into the fraction that they are so supposed to be, or not. Either way is fine. So essentially your y-axis is just going 270 to 0, but it's really 0 to 0.0270. Then we're going to graph. So I know it's a challenge to actually graph these little fractions. So here's kind of my y-axis. This data point here, 6 books of pressure gives you 37 millimeters. 1/37 is this, and that's the top range of my y-axis, and then all the way down. So while you're drawing that, what's the point? What can I find out by graphing this? And
the pressure is increased every time.
Right, but what about negative books? Why do I care about negative books? Is there any pressure on this little syringe right now with no books on it? Is there any pressure on you right now? What?
Well, it's equalized. So I have the same amount of pressure that I breathe in and goes to my body. This is outside by the atmosphere.
Ah, atmospheric pressure. So this little syringe has atmospheric pressure squishing it right now?
It only if it's not the same on the inside.
Well, it is, but that doesn't mean atmospheric pressure is not squishing down on it. It is. So we can actually find atmospheric pressure in books by extrapolating out, right? We can extrapolate that number out to negative however many books. So this isn't actually starting at 0. It's got pressure on it. It's got probably 6 books of pressure on it just from atmospheric pressure. And that's what we're finding out here. I aimed wrong again, Jen, sorry. So, we plot our numbers. So, I'm going to plot 6 versus 270. That is the wrong color for the job. Okay, so 6 versus 270 right there. 5 books, 241. That'll be like there. Your graph will certainly be better. 4 books is 213.
Does it matter which side of the y-axis we put the positive numbers and negative numbers? Like if I have more room on this side, can I use the numbers as positive?
So you're actually going to need more numbers on the negative side.
Oh, okay.
So,
wait, what was that third one you graphed?
So I'm starting from the bottom, so okay. That would be 4 books versus 213 on the graph. That is so bad. 213, it should be a little higher. 3 books and 192. 2 books and 171. 1 book and 148. Okay, so once you've plotted all your, and 0 books and 139. So once you've plotted all your points, of course mine is like a hand-drawn graph and you guys have actual grids to keep you from being all over the place in your drawing. So once you've plotted your 7 points, I guess, we'll draw a best fit line. But take a minute to wedge them in there. And then ideally you're going to want to use a ruler or the side of a book or something to draw your line. Not by hand.
Yeah. That roll?
Yes. And there, or I'll throw the pen. Thank you. So pass the ruler. You boys, there's a ruler back there behind the shelf. Well, 3 of them maybe.
Ew, that's like not connectable.
Oh, okay. Well,
No.
so if you have a few data points that are lousy, essentially what you're going to do is draw a best fit line, which means you want the same number of dots above the line as below the line. Actually, so I'll do it here. Your graphing calculator can do this for you if it's not in my hands, but not when it isn't. So here, probably my best fit line will put a few below and a few above. So I might draw it right there, right? A few below, a few above. And then what I'm going to do is just continue that line and extrapolate it at the same slope so that it crosses the x-axis way down here. 5, 6. So probably somewhere around -7. So 7 books is what I predict atmospheric pressure to be on my lousy hand-drawn graph. There might be blue on this side of this. So. Okay, so yours like lines up pretty nicely. So if you just take a straight edge, line it up, probably like
148
on a slope there, and then just pass it through and see where it hits.
Mine is like off like
Yes, so you're just going to pick a straight line where some points are above and some points are below the line, a best fit line.
Okay, that's better.
So, like, see how that has no points above and all points below? That's not the best fit line.
So like,
I mean, just pick a place where some points are below and some points are above and some points are on. And then, once you have the slope you like, just draw the line.
It is, how?
Right.
Here, you can have that first.
Here.
I don't know how I'm going to do it.
I know.
The data is not going to be.
So, I mean, the
Nah.
graph is pretty straight, but I might.
Yours is straighter than mine.
I don't know. Let's look at
I know
a
where.
straight edge. We'll use a straight edge on that and see.
I think it's here.
That one's below, that one's
48. There we go. I picked 30. No? Yes. That's one of my problems. I don't know how to
Just play with it until you get some above, some below, and see where the ruler crosses the axis. Some above, some below the line.
That's better.
So let me draw it.
And then, yep, and then draw it and see. I mean, 5 is good.
Do we graph the 0 also? 'Cause
Yes,
there's
graph the 0.
very little difference between the 0 and 1.
Mm-hmm.
It messes it.
And that can be definitely problematic. And the reason that we're going to have error right here is because that first book doesn't fully apply a whole book's worth of pressure because it's resting on the desk. Every other book, its weight is going
okay?
down onto it. But you want to cross the negative x-axis. So extend the line, extrapolate down.
did
Oh,
I
wait.
do this?
Like,
Some
those
above,
line
some
up
below.
nice, but that one.
You need to line it
Yeah,
up
you
with
can
that.
ignore
though.
that one if you want.
Yeah, I did.
I can ignore that one completely. It's
You need
the 0.
cross.
Yeah, the 0 might be kind of a bad data
I
point.
think I had the top and public.
So make sure if you have one that's way above, you want to get one that's below.
That's the lowest one right there, the middle one. Like that?
Yep.
Like
And just
that? And all the way down.
zip it across. So you get somewhere between 7 and 8 books of
Did I
pressure.
do this? Right.
All right, so some of you get about 4 books of pressure for atmospheric pressure, depending on how you chose to draw your best fit line. Some of you get around 7 books of pressure. So we have 6 data points, basically, right? Do you feel confident extrapolating out to 5, 6, 7 books beyond your data? No, we're approaching extrapolating about 100%. Do you think that atmospheric pressure probably does exert 4 or 5 books of pressure down on us? Down on this little thing. I mean, we could calculate the surface area of that. I mean, it's probably, I mean, I can measure it. It's like, I mean, it's a cylinder. It's hot pass exposed. Probably like 4 centimeters by 1 centimeter. I don't even know the volume of a cylinder equation. I mean, like, if we made it a rectangle, what, 4 by 1 by
There's cloudy stuff in it.
1? Yes, it's growing like mold. It's horrible. It's old and contaminated. But let's say, I mean, that surface area is 4 centimeters squared, right? So, I mean, we could look up atmospheric pressure, you know, how much per 4 centimeters squared weight a book and see how right we are, right? We're not actually going to do that right now. But we can clearly see that atmospheric pressure really does exert probably 4 or 5 books of pressure. We know there's a column of air all the way up to space pushing down on us, and it really does exert a real amount of pressure. So that's kind of the key point I want you to learn is Boyle's law. You can really see pressure versus volume, where they're inversely related. You learn how to graph, and you see that atmospheric pressure really does exert a real pressure on that thing when there are no books on it. And we can kind of predict what that is. All right, so the last couple of minutes of class, if you want extra credit, you can look back at your Module 6, Lab 6.1. You can fill out that worksheet, or you can throw it out. If you can get that worksheet done yourself, you don't actually have to do Lab 12.1 if you did 6.1 and took the temperature data, which we did. Maddie, what was the temperature that day? It was ridiculous. It was like a super hot day in the classroom. 2014. It was 70. Does it say 70? Oh no, pressure. I'm sure I have it somewhere.
What was it, Lab 6.1?
Lab 6.1. We were supposed to record atmospheric pressure for that day and temperature in the room.
Yeah, really good.
Yeah, some of you definitely had it in your lab reports.
I think this is it. So it was, the circumference of the balloon was 33.35 centimeters. Room temperature was 70.0 degrees Fahrenheit and 21.0 degrees Celsius.
Okay, can you write that on the board right there, temperature and pressure? And then,
You didn't get the atmosphere.
hopefully your lab reports have the biggest volume of gas produced. Now, from solutions, you guys learned about exo and endothermic, right? And we've seen lots of times when we dissolve something and it's exothermic, it gets hot, right? Or where we have a chemical reaction that's exothermic and gets hot. You almost never see endothermic happen. So I'm going to mix these two white solids together. This one is barium hydroxide, and it's a white, flaky, powdery stuff here. You can see, Jen, is that camera pointed? I'll come over there so I'm not doing it over my teacup. Barium hydroxide is not your friend. So white, flaky powder. This is ammonium nitrate.
Very white.
It's like little white balls. So when you mix two white, powdery things together, what would you expect to happen?
Need a lot of white powdery things.
Yeah. Would you expect there to be a chemical reaction between two white powdery things?
No.
No, strange, huh? Two solids. It takes a while, so hopefully you guys can hang out for a minute. You can swirl and pass it around, and you can feel if it gets colder. So pass it back and forth and just feel and swirl and pass. When it comes back to you, it'll be different, so
Why can't we
observe.
make something that's hotter? It's cool.
We know how to make hot things. That's easy.
Oh, cool.
This is an endothermic reaction.
Doesn't make white powdery stuff. It's terrible.
Don't smell it.
By accident.
Ammonium
Stupid.
anything is going to make you sad. So it's starting to get slushy.
Yay!
See the slushiness? And does it feel cold or hot?
It was bad.
If you want to smell it,
I
y'all
mean, I
know what
didn't
ammonia
purposely
smells
do it,
like, so
just-
there's no need, but you waft. You waft, you don't go.
Pretty sure that's what Jenny did.
Yes, she did. Smelling salts are a form of ammonia that certainly wakes you up. If you didn't get your caffeine today, go for a little walk. It's cold. So not two white powders and definitely cold. Endothermic.
I'm going to be seriously injured.
Yeah, wafting. We're wafting. And then Jolene, who definitely had nothing like this when she had it before, can.
Is it going to kill my answer?
Isn't that amazing? No, you'll be all right. Yes, it stinks really bad. We'll leave that all through physics and let them wonder. So, freezing cold.
Get in the corner and like wait for them to figure out.
They all, well, except Eric, they all took the class, so cold. So endothermic processes. So here's the fun part of endothermic processes. So think, exothermic gives off heat, right? So what happens to the energy of the products? If they lose all their heat to the environment, what happens to their energy? It goes down, right? If you lose all your heat to your surroundings, your energy goes down. How about endothermic? It takes in heat from its surroundings, so the energy of the products goes up. So the energy of the products is higher than the energy of the reactants for endothermic. Lily.
The atmospheric pressure wasn't recorded.
I recorded atmospheric pressure, and I will email it to you, and now I'm writing that on my hand. So here's our horrible smelling slushy, freezing cold. Hold on.